Alright, time for another draftphysics.com, debatephysics.com also, but no physicist will discuss or debate or even argue what they state to be their truth. And they do state it as a truth, as if they have sufficiently resolved the issue, and there's nothing more to say, and you just have to believe what they tell you, and blah, 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 blah. And they do it in this pretense of being well qualified, spending years studying, and but it's really just they say so. When you really look at it, when you really look at the evidence, they really haven't done any of the experiments, frankly. They'll do a whole formula and tell you the answer, and yeah, they never proved it with an actual experiment, which is quite pitiful. So I'll just illustrate the simple argument against. They have a kinetic energy theorem that says that energy of an object is some sort of scalar function. So it's not really its motion, it's some other something associated with their motion that doesn't have a direction. They think speed is not directional. So anyway, I mean, I know it sounds too crazy to be true, but yes, that's what they state. And the simple arguments against it, I've gone over dozens of them. They're listed on the debate website in little 5-minute chunks, and they won't debunk any of the statements I make in those videos or demonstrate them with evidence to be untrue. So you can have a simple experiment. You have a 5 mass object going 10 velocity one way, a 10 mass going 5 the other way, and you have a little tug of war. You tie a string between them, you let them go out, and when the forces are when the math is done by nature, it says one of them doesn't have more energy than the other. They both stop and wobble and do stuff, but the one that's supposed to have twice as much energy will not drag the other one with it. And it clearly won't do that in the case of what they claim to be true in gravity. That is, 4 pounds dropped 1 foot is the same as 1 pound dropped 4 feet, which is only twice the velocity. So 1 pound with twice the velocity is not going to be the same energy as 4 pounds at one velocity, and the 4 pounds will drag it. Okay. And those are simple enough experiments, really dirt simple. I think they know the answers to them. Just as I think they know it never takes 5 to 25 times the fuel to spin something 5 times as fast. And that spinning it 5 times as fast does not mean it has 25 times the torque or capacity to do work. So rocket engine's huge giveaway. Momentum is creating the equal and opposite reaction. It's just about how much momentum is in your thrust. That will decide how much momentum you get into your rocket, and there'll be no sign of kinetic energy working at all, doing any work at all. So this is a NASA scientist, worked 15 years or something for NASA. He's become a teacher now, I guess. I don't know whether he did actual teaching for a while. I don't know that. But anyway, makes lots of videos, and I'd say, on balance, they're fairly good if you're a Catholic. I mean, if you want to hear the religious story, he tells it just as good as anyone else, but it's all just made out of crap, and I'll point out the crappy bits as we go through this basic conversation about physics in general and the different elements of physics, and his brief description of what has been accomplished, and I'll give my brief description of the real facts and truth. That the physics is garbage, that they're teaching garbage, and they won't respond. They don't have the integrity to defend their physics against the accusation that it is just garbage. They're essentially they're exaggerating false narratives is the most polite way to say it, but what they're really doing is just proselytizing a religion, a completely irrational, illogical, faith-based religion. So, just check the volume. Sorry, should do that ahead of time, yeah. So much to do, so few of me to do it.
Hello, welcome to the Physics 1 course, Unit 1. This lesson I'm going to
Auto and diesel.
Gee, that's disappointing. Yes, that's awful quick. Alright, should be back.
Introduction to Physics. So what I want to do in this lesson really is to spend the next 15, 20, 25 minutes, however long it takes.
I wish you would take however long it takes to really explore all these subjects in depth. So you all say the same thing. So you've got 4 million videos that all tell the same story, and none of them really go into any depth in terms of really challenging and poking at the evidence and pointing out what experiments have and have not really been done, and the rest is just exaggeration. You know, we did the electron double slit experiment, some kind of nonsense, when that's not what they did.
To give you, number one, a motivation for why you even should care about learning physics. I mean, some of you may have to learn it, but why should you care to learn it? But secondly, and what we're mostly going to be doing here, is getting an overview, a broad overview of almost every topic in physics, which seems to be an insurmountable task, but
Yeah, it really isn't. I mean, you know, when you really, I mean, if you had the right story, it would be really simple. See, you have a complicated story with gods and holy ghosts and what was it? Oh, messiahs. Yeah, and messiahs. If you really broke it down into what it really is, which is just masses moving, okay, momentum, and it's different forms of momentum, little tiny bits of momentum versus big giant chunks of momentum. But it's all just momentum. It's just little stuff pushing other material objects. And that's all there is. And if you had it that simple, then it'd be really simple because it's only one subject then. Everything is based on the one function, which is charge. I mean, the fact that the little bits are red and blue means it's the same as the matter bits, electron, proton. See, the force matches the matter, and that works really well. So there is a simulation demonstrated at the DraftPhysics.com. You can get a video there called Simulation, and it shows you how simple it could be. But they won't hear of it, they won't look at it, they won't pay any attention to it, because they're just preaching a religion. And evolution doesn't mean anything to them. The truth doesn't mean anything to them.
we're going to take kind of a tour of the main concepts and the main ideas in physics to give you kind of a roadmap of what we're going to learn in this entire class.
Dualities is all you're going to learn. Momentum and kinetic energy, scalar and a vector, particle waving, or waving particles, and blah, blah, blah. You know, duality. Bent space, time, which is nothing, and it creates energy from nothing. It's all bullshit.
All right. So at the end of this lesson, you should know not only why you should care, but you should also understand some basic ideas about.
Yeah, well, see, he's a NASA scientist. I say you should know that the Earth is hot because of gravity. The gravity is making it hot in the core. It's melting the Earth. You should know that. No, you really should know that. And that's free energy, right? By your theory, because you don't have any theory that puts the energy back into the bent space. So you should be able to figure out that your theory is non-conservative and nonsensical because you have this two different, completely different descriptions of reality. You have mechanical parts moving, and then you have this, bent space thing that makes things move without any mechanics.
What is physics? What do we care about and why?
Yeah, it should be about physical things that take place in our universe. And the universe is made of things. They're physical, and they have physical interactions. It's not a religion. It shouldn't be, okay? There shouldn't have any magic in it.
Why do we learn it, and what main topics are inside of the class that we call physics? So the first thing is physics is all around you. It's one of the sciences that you can walk outside, get bathed in.
Well, see, that's, that's sort of true, but it's really not, because you have to use all of this, people 1,000 years ago couldn't really figure out that, okay, there's all these invisible forces, there's radio waves going through me, there's starlight, there's all kinds of gamma rays, and all kinds of different rays are hitting me that I can't even see, the ultraviolet, the infrared. And then they certainly couldn't understand that the real material part of my body is really just electrons and protons, and when you poke on this, you're poking on the electrons, and that's why it moves, is because the electrons are the barrier. They're the the thing, the glue that's holding it together. They couldn't know all that. And you can't just go outside and know all that.
In sunlight, drive down the road in a car, or whatever, and
Yes, you can do all that stuff, and that stuff seems pretty intuitive and pretty direct in its statement. It doesn't take 25 times the gasoline to go 5 times as fast in the car, and that's just the truth. And then you could do it lots of other ways. The 8-pound bowling ball going 16 miles an hour will not knock down more pins than the 16-pound going 8. So that's a giveaway. The ballistic pendulum can't collect any more than 0.06% of the kinetic energy. Well, that's a huge giveaway that energy can't be worth much. Can't do any work with it. Can't move a spaceship with it.
you are experiencing physics in almost everything you do.
So you're not experiencing any of their quantum entanglement, any of this superposition crap, any of this bent space crap. You're not experiencing any of that nonsense.
Things like light hitting you on the skin, heat,
Yes, that's momentum, right? Light has momentum. It has a mass and it's moving a very fast velocity. So it has a very tiny mass and it's moving a very fast velocity. And the particles that make up light, a photon, are carriers of energy. Just a fact. They're the things that make matter move. The matter, electrons and protons, have no motor. They can't do anything. They have to collect force to be going somewhere.
radiation from the sun, electricity, magnetism, radio waves, motion, the work that is done by the car, from the gasoline in the engine pushing the car. All of that stuff is physics. So one of the main
Push is a key word here because, yes, that's all there is. The only contact you can have is push contact. There's no pull contact. There's no way to make something pull it without pushing it inversely.
reasons why you really should care about learning it is because literally everything you do every second of the day is impacted by physics.
Not your physics. Newton's physics, yeah. Your physics, no, not so much.
But I personally want to convey to you the big picture of why you should learn physics and why maybe you should take an interest in it. And that is because for hundreds of years, really thousands of years, humans have been trying to understand the world we live in.
Right, and you're not trying anymore. You've written your silly fable, and all you have been doing for the last 100 years is preaching the fable. And again, you haven't even done the tug of war, between these things that you say are equalities. You haven't even bothered to do any elemental experiments. No car crashes, no nothing. No, let's see how much gas it actually takes to go 5 times as fast. You haven't tested any of it.
We don't have all the answers. Even in this physics class,
We don't have any of the evidence. That's the problem. You don't have any of the evidence. And that's what you should have. That's what science is supposed to be, is deduction based on facts. You're supposed to find a real knife at the scene or a real gun. Okay, and then you're supposed to do a ballistics test and all this other stuff. You're not supposed to just draw a picture of a gun and say, see, look, he killed her with this picture of a gun. You're not supposed to do that.
don't have all the answers. But we have amassed a great deal of knowledge about how things work.
So not really. Now, I mean, there's some, obviously, electron microscope, good invention, lots of things that were helpful in seeing things, but none of it saw the crap you're saying exists. It's still you telling us that there's this wacky verse, and that the photons are randomized and that this happens and that, and they bang into each other and they disable each other and they do all this crap that we know can't happen.
So I want you to kind of think about 200 or 300 years ago when there was really no electricity in your lab or in your house, and there was candles burning, and you were just struggling as some person in 200 years ago to understand what magnetism was, or to understand what a chemical reaction was. That's more in the realm of chemistry, but chemistry and physics are like peanut butter and jelly. Or if you were trying to understand what heat really was, and what work really was, and what energy really was, and you spent your whole life trying to understand those things. And
Right, and Descartes told you the answer, which is basically there's this stuff, energy, and it moves through the universe, this activity, this notion of movement, and it's just a bunch of movement in a sealed container. We're in a fish tank of movement. And so if the movement isn't here, then it's over there. It's always somewhere. Okay, and you don't ever destroy it. It just keeps on moving from thing to thing. So even when you do some work, the end product of your work, after you've used the energy for a little period of time, the energy keeps going somewhere else. It always dissipates into some other object. And it tends, from our perspective, it tends to go from consolidated laser beam into diffracted and spread. But then gravity fixes all that, and gravity takes all of the diversified energy, all the spread energy, and consolidates it again. So now you can make it into little beams and such.
Scribbling down equations and going down one dead end and coming back to try a new path, right? So you would, for lack of a better word, you would do almost anything back then to understand what you now have the opportunity to understand.
Yeah, so he's talking as if they've explained something, and they haven't explained any, all the big questions are left kind of open, and Darwin solved the only one that really mattered. So, once you know your bugs, and you're just trying to figure out how to be a decent bug, and that's all there is to do here. I'm a calculator. Is there anything to calculate that's worth calculating? And the truth is, no, not really. Just calculating how to gracefully exit, frankly. Because the whole thing is just a slaughterhouse.
Because of all of those people that came before you and devoted their lives to try to figure this stuff out. One example would be Isaac Newton. I know you've heard of Isaac Newton. We're going to talk about Isaac Newton for a long time.
You're going to slander him, basically, okay? You're going to put words in Newton's mouth that he didn't utter, and you're going to put concepts in his vocabulary that he didn't have any idea that could possibly be reasonable. So Newton didn't draw conclusions. He didn't jump the evidence. You guys jumped the evidence. You jumped to your wacky conclusions. Newton says, I don't know. I think that's a good idea, and I think that's interesting, and I think this is interesting, but I don't know.
Time in this class. Well, you know that he has his famous laws of motion. What you may or may not know is Newton is the guy that invented something we call calculus today, which is an advanced branch of math, right? So this is a person.
No, it's interesting. Calculus isn't all that. They keep talking about calculus as like it's the key to understanding anything. No, it's not the key to understanding anything that matters. If you want to know something minutia, you want to know minutia, like, we took this jiggity path, and my left foot stepped off the sidewalk once, and then my right foot stepped on the other side, and I had some dog dew on it, and I slipped a little. And you want to know exactly how that changed your miles per hour. Okay, well then calculus might be of some value, but if you don't want to know any of that nonsense, calculus opens no insight to the functions. It doesn't explain electrons, doesn't explain protons, doesn't explain charge, doesn't explain magnetism, doesn't explain a damn thing. So it's just a bunch of hype.
Person that was trying to solve a problem, and instead of...
So, and again, Newton didn't need calculus for most of his observations about how the universe works and to make his proofs about ellipses and different arguments. He didn't need to use calculus to make those arguments.
Just giving up because he didn't know how to solve the problem. He invented the entire concept of calculus. The thing that everybody learns takes many years to learn. He invented that himself.
No, so everybody learns it because it's math, and physics is really about doing math instead of about understanding concepts and understanding what a paradox is and understanding what a contradiction is. Now, scientists should really understand what contradictions are and paradoxes, and they should be avoiding those things like the plague, because that means you have a bad idea. Okay, when those things happen, your theory's broken, and they couldn't care less.
For the purpose of solving a problem he was working on, right? But even Newton, as smart as the man was, as brilliant as the man was, would probably do almost anything in his day to have the knowledge that you had.
So the idiotic Einstein field equations he wouldn't find very useful, I don't think. He would have just called that meaningless minutia. Obviously, whatever this change in Mercury is, it has to do with how close it is to the sun, and it doesn't have anything to do with anything other than how close it is to the sun. So the sun is doing some little thing. The sunspots. Maybe the sun has a planet inside of it. Yeah, maybe it has hard bits inside of it, clumpy bits. And that can perfectly explain the precession of Mercury. So, the whole thing is just a fable that you need to change Newton because Mercury moves 4 feet different year to year. I mean, it's just such a pile of crap.
Today, because of everything that Newton did and everybody that came after him contributing to this knowledge, he probably would just dream that you could watch a video or.
Oh yeah, I'm just saying I don't think there's any chance that Newton would be on Einstein's side. Okay, he'd find all of your gibberish to be just that gibberish, and he would be mad at Einstein because he'd say, "What is your theory but spooky action?" What, you don't think Isaac Newton, could come up with some dopey explanation like, the bent thing did it? Yeah, I bent it. The thing that doesn't exist, I bent it. That's what did it. You don't think he could come up with some wacky, silly, perfect explanation in the sense it's the Invisible Man explanation? There's no way to test it. Okay. And you think Newton would be fooled by the fact that, oh, you're saying atomic isotopes that a clock can't be broken in any way? I can't change the half-life of a decaying particle? I think he would know that, oh yeah, I can. All I have to do is concentrate it. All I do is change the concentration and I'll change its decay rate. So what have you don't have anything demonstrating this bent geodesic exists, and then I can make the rational counter argument that clearly the gravity's creating momentum. It gives things momentum. That's energy, and it has to be accounted for. Where did it come from? How did you put force into something? All right, and now its force, like Descartes says, its force is going to continue to fly around in the universe. Well, how does the force go back into the bent geodesic? How does it get back into the bent space? I mean, it's a complete lack of logical continuity. And the fact that I have to explain that it's a complete lack of logical continuity to a NASA scientist is kind of freaking amazing.
Take a class or solve some problems and learn all of this stuff and all of these topics that I talked about: magnetism, heat, and then the more modern things like relativity and quantum mechanics. So what are my...
But don't dare, okay, do the logical thing and say, hey, he's right. What about this gravity thing? I mean, how can you make bent space makes energy? Clearly, it makes things have energy. Well, how is that not free energy then? There's got to be some way to put the energy back in the bent space. So why don't you explain how that takes place?
My expectations in this class, what do we want to get out of it? I want you to be able to solve problems.
That's all it's about. Yes, just do your math, okay, because math is fun. So, figure out how many moles of nitonium you can fit inside, in between the air molecule layers between your toenail and the skin. Yeah, that's a really fun thing to figure out, isn't it? Oh, I can't wait. Oh, gee, it's going to be such a fun thing to do. No, it's a waste of frickin' time.
I'm definitely going to lecture and I'm going to tell you the concepts. Concepts are probably the most important thing.
Right, and that's what they got all wrong. Every time they had a concept, decision to make, they went the wrong way. Wave particle, momentum versus whatever K. I don't even know what. Living force. Yeah, momentum versus living force.
But equally important with that, or maybe even more important than that, in my opinion, is to be able to solve a problem. Like, you can understand.
Right. So solve it, get an answer that's completely wrong. So you'll do your equation and say the rocket thrust has 4,684 joules of energy per second. And then you'll figure out that the rocket isn't moving that speed. So the rocket doesn't have 4,000 joules of energy. So it's not obeying Newton's third law. So what does obey Newton's? Oh, that's right, the momentum obeys Newton's third law. People are just so full of crap.
the concept behind something. But if you can't get your pencil out and you can't solve a problem, then you really don't understand anything.
Right, so they'll get their pencil out and they'll solve a problem. The simple little question I asked, right? 5 mass object going 10, 10 mass object going 5. Have a tug of war. They'll say the 5 mass wins decisively and drags the 10 mass, to the poorhouse. That's what their math will say. It won't happen in reality. And again, their math will say, how much fuel do I need to increase my velocity by 5? Well, the math will say, hey, 25 times the fuel. Yep, that's how much it takes, 25 times. Yep. So they don't care whether they get wrong answers. They just give you an answer and say it's right, and they never prove it. They never show it to be right.
Really, in my opinion. So this whole class is going to be problem-based. We're going to lecture, we're going to get concepts and ideas, but we're going to put pencil to paper and we're going to solve problems. So
with nonsense formulas that aren't real. And they're going to say something like, look, a Newton is 100 grams. That's how much it's a weight. That's all Newton is. And yet they'll say it's a meter per second squared or something. Or a kilogram per second. It can't be a kilogram per second squared, but then 100 newtons would be a lot. Well, anyway, whatever. I mean, they say some nonsense, right? So they describe simple things complicated for no good reason. A newton is 100 grams. A joule is a kilogram. It's a weight.
My advice to you is to keep in the back of your mind, every one of these concepts are easy to understand. I can explain every concept in physics to probably a third grader.
Says you. So again, none of this convoluted nonsense mathematical relationships can be explained. And again, you can't even explain the simplest things correctly. You're comparing water waves to the pattern created by photons, and you don't even recognize that, well, there's no double maxima, they're not spaced the right distances, the bright spots are lighter than the dark spots, or bigger than the dark spots, there's only a certain possible amount of angular places you can get a wavelength of difference in the lines anyway. I mean, you're doing all of it's nonsense. And then you're going to explain something like entanglement? Bullshit, you're going to explain that nonsense.
Basic overview. But solving problems tends to give students a lot of problems because their math skills might be okay, their concept, they might understand the concept, but putting the two together...
Oh, that's just ridiculous. They either don't know enough about this trick math you can do, all of this equals this, and so we'll turn this into what this equation says it equals, and, it's all distortion, and, it's all a 3-card Monte, shell game.
Reading a word problem, figuring out what is important in the problem, writing down whatever equation you're trying to use and applying it correctly is very hard. And the reason it's hard is because it takes practice, just like, running a marathon takes practice.
Right. You have to just memorize silly notions of, well, in this circumstance, when they want to know this thing, I use this equation because it, almost works. But I can't use it when it's moving, and I can't use it when it's raining, and I can't use it when some other variable is involved because, yes, it completely doesn't work. So you can't use MGH to find out how much a moving object is going to be affected by gravity. An object moving in the same direction as the gravitational force. If it's already moving, your theory ain't going to work.
Or learning how to, play basketball or football takes practice. Solving physics problems really just takes a lot of practice. But once you do it, you will definitely get better at it. So my advice is, as we solve our problems here, please watch me solve it.
Okay, so the thing you have to watch for is there's real equations that have solid foundation, and then there's mush equations that have no solid foundation. And so that's the real difficult part, is figuring out which ones are well grounded and which ones they just made up. So again, if you use kinetic energy to decide how much rocket fuel you need, you're not going to get anything close to a right answer. You're going to be way out of luck.
Make sure you understand it, but then pause the lesson and get your own paper out and solve it yourself. Even if you've just seen me solve it just a minute ago, you going through the motions of solving the problems is definitely going to help you. And the final thing I want to get to before we get into the overview of physics is that anybody can learn this stuff. Anybody. Okay? The only thing we're...
Yeah, whatever. Take a break and such. Yeah, just a little context. I mean, I did contact this guy in the past, maybe a year and a half, 2 years ago, and, you know, politely, and just tried to get him engaged with these subjects a little. He wouldn't respond. So, you know, in a useful manner, just said you're wrong and you're a kook and you're a flake or whatever, just the same old jargon. And so, yeah, I have no obligation to be polite anymore. So, and again, he's a NASA scientist, right? And so he should know the Eddington experiment is bullshit. Never repeated from Earth beyond the margin of error. And, you know, we have at least a half dozen satellites right now looking at the sun, you know, measuring different things. And to tell us that, oh, yeah, we can't use any of those satellites and just move the camera to the left a little, or move it up, that would be more interesting. Just move it above the sun. And let's see if we can watch a bunch of little stars go all wacky. Yeah, really easy to do from space. And it's never even occurred to NASA to try the experiment, huh? I mean, it seems lame as hell. I mean, there's really no good excuse for them not doing it because it'd be fascinating. And the reason why they're not doing it is because it's not going to work. Because the theory's crap. Light isn't bent by gravity. It don't happen.
Required is the willingness to learn and some basic math skills. And when I say basic, I mean you're going to have to know...
Light can't have two motions, okay? Like baseballs, you can move them in 3 different dimensions. You know, you can give them a velocity this way, you can give them a velocity that way, you can give them a velocity, you know, forward. So you can give them, you know, velocities. But light can only have one velocity. It can only move one vector. It can't be going this way and get pushed by gravity that way. Can't happen. It's a one-dimensional object. It cannot do 2-dimensional motion or 3-dimensional motion.
Some basic algebra, which I will review along the way for the most part, but you'll need to know some basic algebra, some basic trigonometry. We'll talk about angles and triangles. I'll try to review as much as I can, but you really should have some basic skills in those areas.
Yeah, that's an interesting subject, actually, just because, you know, they turn everything into this cosine and sine, and they could just leave it Pythagorean. They could just say, understand the triangle on the 2 sides and the square roots. You know, the square root of the squares of the sides will tell you the hypotenuse, and you know, that'll work. But instead, they like to use sines and cosines, but you have to go look those up. You know, I don't know exactly why that is.
And ultimately, you need to be able to put in the effort to solve problems yourself, even after you've seen me solve them. The final thing I want to talk about before we get into the overview is that we don't have all the answers. We're going to present...
He keeps saying it, but it don't. No. Obviously, he'll tell you the next minute that, well, it's well established and we've proved to the 900th decimal point, and we've done this, and it's the most proven theory in the history of mankind, and blah, 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 blah.
Present all of this stuff as if humanity has figured everything out. But I want you to know that we haven't figured it all out. I'm telling you right now, people are doing research in advanced physics trying to figure out what mass is. You know, this marker has...
So that's the silly part, right? so you know, it's laughable, right? Because we know what mass is. We know it's electrons and protons that have to be pushed. That's what makes an atom. A neutron is an electron and a proton. And those are the constituent material objects that have to move when something moves. So when something moves, it's how many electrons and protons it has will decide how hard or easy it is to push, because you have to push it, all of that mass. And that's the simple argument. That's what mass is.
Some mass, right? We say it has mass. You all have an idea about what mass is, but people are doing research today trying to figure out what really is mass. Right? Why is it harder to push something that...
You know, that's so intuitive and so sensible, right, that I don't think that even bothered Newton at all. Why is it harder to push big things than small things? I mean, that was just like, well, obviously because it's less of it to push. Obviously, if there's more stuff, it means there's more little bits that have to be given the force. I have to share it with more little bits of stuff. So the quantity of motion idea... The idea that this is a substance, energy, and that you have to give it, you have to spread it over the bread, so to speak. Oh yeah, if I have to spread it over a big piece of bread, it's going to be very thin, so it's going to be very weak movement. If I'm spreading it over a small piece, it's going to be very thick, lots of movement. Not hard to figure that stuff out at all. So, I mean, this is also revealing that he would suggest that mass is one of the complicated questions when that's a non-question.
Has a lot of mass. Why does that happen? How does the universe know to kind of resist your pushing?
So it doesn't. There's no resistance. It just says, give me the money and I'll put it in the little slots. But you have to give me enough money to put in all the slots, all right? If I have nickel slots for each atom and you only give me 5 nickels and I have 10 atoms, well, I'm not going anywhere because there's not enough energy to get all of my crap moving. I mean, that's not hard to understand.
Whenever it's a big heavy ball or a boulder, and I can push something that has less mass. I mean, we take those things for...
Yeah, yeah. So there's nothing taken for granted. I'm just saying this is one of the most, you really can't go wrong intuitively, just because it's just so obvious that what you're doing is applying something to something, and the more of it, the more you have to apply. I mean, it fits with every single circumstance there is. You can't fill up the bucket. You can't fill up a 1-gallon bucket with a half-gallon of water. I mean, come on. Not complicated.
Granted, but the physical mechanisms that underlie all of this stuff in reality is not trivial. It's not something we all know the answers to. So,
well, some of us know the answers. Okay. So at least one of us on planet Earth has got the right theory and model to explain the function. So, and the rest of you are just religious kooks, frankly. Because again, it wasn't that hard. Once you detach yourself from believing any of their crap and just go back to what Newton knew and Descartes knew and Galileo knew to be true, and just start with that foundation, it won't take you all that much work to figure out how it works.
you learn on this stuff, learn it, but keep in mind that as you kind of get older and you study more, there's always going to be more stuff to learn and more stuff to contribute. All right.
So bullshit. There's nothing to contribute because you built a pile of horse shit. Okay, so there's nothing you can build on manure, all right, or quicksand or mush. Okay, it's a pile of mush. So you don't build on it. You fill in the mush hole and then you start over. You start with a good foundation. And that's what Newton, Galileo, and Descartes gave you, which is a very good foundation, and you turned it all into shit.
Physics in general can be broken up, I'm going to break it up, into 3 main things. There's physics, typically you take physics 1, and then there's physics 2, and there's physics 3, right? So what do we cover in physics 1? I'm going to expand.
Yeah, I guess the MIT calls it 100, and then 101, and then 102.
And on this stuff, over the next several minutes. But essentially, physics 1 are all of the concepts associated with motion. Motion.
What it really should be is interaction. Concepts associated with interaction. Because the motion isn't relevant until there's an interaction, frankly. And it's just about what happens when there's an interaction.
Force and energy.
And none of those things can be exchanged without physics contact. So there is no magical pull force. There's just banging something into something. And in some respects, negating a force. Taking a force away is the same thing. It'll create a disproportion in the force. A balanced force becomes imbalanced. But it's still, the object isn't going to move because it was pulled. It's going to be moved because you removed a push. Push-averse.
Now, everybody watching this has some idea of what motion is, things that move, right? And what a force is when you push on something, right? And energy.
Yeah, so they should say maybe weight to understand a force is pressure created by weight. And that's momentum. So force should just be called momentum, clearly. They all should be called the same thing because it's all the same thing. It's all momentum. It's all weight. It's all just pressure. And period. All interactions involve competing pressures.
You might have an idea of energy, but that's usually a little bit sketchy, or people aren't quite sure.
Yeah, because you have that silly statement where you're saying the word energy belongs to 1/2 mv squared and momentum isn't energy by your theory, when clearly by Newton's theory it was energy. That's energy. The definition of energy for Newton would have been, of course, quantity of motion, momentum.
What energy is, but we know it has something to do with motion or with doing something, that kind of thing. And that's typically true. But the idea here is we're going to drill down into these areas, and we are going to...
He really ain't going to drill very deep. Okay, so he's going to kick the soil a little. He's not going to, he's not going to reveal any of the truth. Blow a little dust off. That's all.
110% go...
He's not going to go into all of the defects in their theory. And the first defect starts with Leibniz, and then Deschardelet and the silly experiments that had nothing to do with being scientific. And then all the way to Joule, who, instead of doing the tug of war experiments, decided to drop things in gravity. And drop them at different speeds, and then presume that they somehow had the same energy. They collected the same energy no matter how fast I dropped them, which really was a very flawed conclusion to draw.
Into every one of these topics.
Especially when it's a 9.8 meters per second, 1 second force. It happens every second. Not some other amount of time, just every 1 second, 9.8. If it's going to be 2 seconds, well, then it's going to have to be 19.6. And if it's going to be a half a second, then it's going to be 4.9. Yeah, see, the number changes if you're going to change how much time. So you have to use it in 1 second units.
Topics and define them to understand what we mean in physics by force, motion, and energy, so that when we solve our problems, we know what we're doing with each of our equations, with each concept.
The key to great skin is exfoliating and moisture.
Nah, sorry. Alright, should be back, so leave us continue.
Now, typically after you finish all of this up, which is quite a bit of material, we're going to get into more detail about that in a second, you talk about physics 2. And these are arbitrary definitions, but typically in physics 2, you learn about a big word that scares a lot of people. It's called thermo. What do you think thermo means? Like a thermos, it means heat, right? Or temperature. Thermodynamics. Whoops, I can't spell dynamics. Dynamics. Right? Thermodynamics and waves.
Strange combination, right? Just too silly almost. So anyway, I don't know why I throw waves in. So waves really doesn't have anything to do with physics. Frequencies do. Periods do. Cycles do, but waves, no, not so much.
So in the broadest sense, physics 2 is going to be about dynamics means changing, thermo means heat or temperature. So it's all about things that are changing.
So it's just a way of recognizing that the elemental substance is discrete and small and tiny like heat. It's vaporous. That basically you're just talking about how that migrates through the environment. And the fact is that we're hot, the planet's hot. From absolute zero sense, there's lots of action and things moving around inside of every material body. And all of that movement is created by the fact that there's stuff hitting us going both ways. And it doesn't cancel. It has to turn the wheel right, and then turn the wheel left, and then turn the wheel right. And everything is at a kind of thermo equilibrium. And that's the more important concept, is that you can't destroy this thermo stuff any more than you can destroy energy. And therefore, it's the same thing. The heat is the energy, just in tiniest form.
Changing heat, and also what kind of work can we get out of that? So you think about it.
So work is just a fake word for what kind of use can we make of a stream of energy. And the simple idea is that we can only make use of streams of energy. When the energy is diverse and spread hard for us to make a collector. But when the energy is moving down a stream of water, for example, we can steal it. And we can poke our fingers, so to speak, into gravity and steal the stream of energy. So there's places where we can take advantage of the fact that there's an existing stream, flow of energy, and we can take advantage of those flows of energy, where it's hard to take advantage of it when it's discrete and diverging.
Car engine,
Convergence, easy to capture. Divergence, harder to capture. Something like that.
combust gasoline in the piston, right? Or in the piston chamber.
Right, so all of that has to do with the compression of mass. Just like gravity, the mass is compressed. That's why the atoms are made inside of suns, is because that's where they can be compressed. And then in the environment, we can release what has been compressed.
That explosion releases heat and it pushes that piston. So the concept of heat, which is coming from that explosion, right? And the concept of the piston moving, which is doing work able to push the car, those are interrelated things. So thermodynamics is all about heat energy. How do we transfer that into work that we can do on the environment? How can we build?
So the heat just really has to do with expansion and contraction. So you're just taking advantage of the fact that you can take advantage of the flow of energy that presses and compresses something, and you can take advantage of the flow that's also expanding.
Build a machine that somehow uses heat energy and get it to do some work. And there's a lot of details there that we'll get to. But that's what it
Yeah, so heat doesn't really do the work. The stuff the heat changes does the work. So heat affects matter, basically, expands it, and or contracts it. I mean, you're either doing one or the other function to matter when you apply heat.
basically is. And we talk about waves. We have water waves, we have sound waves, we have energy that we can transmit via a wave.
So sound waves are completely different than water waves, but it's one's a truer compression, the other one is a non-compressible fluid, and one of them is a compressible fluid, atmosphere. So in that sense, very different.
If I get a jump rope and I kind of oscillate it, I can send energy down the rope to impact a wall or whatever it's tied to. So we're going to talk quite a bit about waves. And then we break up the class into Physics 3. Physics 3 is actually my favorite part of physics, but I like them all. But Physics 3 is my favorite part, and that is electricity and magnetism. So electricity.
Later he says something about his favorite part being quantum electrodynamics and quantum mechanics, and so not exactly electricity, but anyway.
And magnetism. There's some other topics in here. Now, when I say electricity, we are going to learn a little bit about electric circuits, batteries, circuits, voltages, current, electric current, things like that. We're going to talk about that. But really, the main part.
So this is kind of now a messed up subject in the sense that, there's still this existing statement by Veritasium that somehow, the electrons moving through the wire aren't doing the work. That somehow it's the radiant process, the magnetic process, that's actually lighting the light bulb or something. And clearly nonsense. The induction isn't running the system. The system has to be run by the actual physical electrons to have enough power to actually produce anything significant. The thing they're not getting is that the electrons are like photons. In a sense, they're just momentum carriers in the circumstance. You've got them stuck inside of a tube, like a fiber optic tube even. So you can control the electrons and where they end up going and pushing. And so it's the same thing, basically. It's just momentum in this more discrete form of moving electrons rather than moving buses or cars or people. You're just moving electrons. And there's rules, and The rule is that when electrons are moving through atoms, where they're exchanging their electrons, or the pressure of their electrons, the atoms are changing their polarity, meaning the electrons and protons show differently. And when the electrons are in different positions and the protons with the protons, it produces a different pattern, a different view to the world. So when an atom is in its neutral state, maybe it looks yellow and brown, and then when there's electricity, that is when electrons are pushing through it or it's exchanging, it switches from, it ends up going brown-yellow. I mean, yellow-brown. It reverses the image produced. It's a simple way to put it, and that's what's creating the induction, is the mere fact that the wire, if we had the eyesight to see it, is changing its polarity pattern. And that's the magnetic signature. But it's all in one single field of energy. The electrons and protons are constantly pushing, compressing parts of that energy, reducing the frequency and expanding the frequency, increasing the frequency and decreasing the frequency. Yeah.
Of electricity and magnetism, we're going to learn about magnets. We're going to learn about the magnetic field that surrounds a magnet.
So there's no magnetic field, there's just the field that's around everything that's causing gravity, magnetism, photons. All effects are created by this field. Photons are just the field at a pattern. Magnetism is just the field at a pattern. And that's all you're doing is changing the pattern of the reflections you produce. You're at thermal equilibrium, that is, as much energy is going in as coming out, unless you're changing your state. And all you're doing is changing the look of the energy. It goes in looking one way, it comes out looking another way, but it's the same amount of energy, thermodynamically.
We're going to learn about the electric field that surrounds an electric charge, like an electron or a proton.
So they don't have any specific field. It's just one field of energy, and they react to the pieces of that energy in an inverse way, which creates the obligation for electrons to repel and protons to repel each other, and electrons and protons to attract. They're not really attracting, they're just mitigating against the force that would exist if it wasn't for the properties of electrons and protons that change the nature of that force. But it's the same amount of stuff moving.
Some other charged particle. So we have this thing called electric fields and magnetic fields, and they're kind of like peanut butter and jelly. They're not exactly the same thing, but they're definitely related, and the equations that govern both are very similar to one another. So really, in modern physics, we've unified.
The point is it's all unified, and they haven't even come close to truly unifying it, because it's not a bunch of different fields of different forces of different functions. It's one type of stuff moving the speed of light, and the matter that is pushed by the stuff moving the speed of light. It's that simple. All motion is the exchange of force, bits, those little things there.
Electricity and magnetism into one thing called electromagnetism. And it turns out if you take an electric field and a magnetic field and you oscillate them.
So again, there's no fields, there's just patterns in the energy you're reflecting. And you can change the pattern of what hits you by delaying or expediting when you readmit the energy, how you change, how you affect it, how you reflect it.
So that they're kind of a combined oscillation. What you end up getting is an electromagnetic wave. So it's a wave.
So there's no waves. It's all discrete, independent little bits of energy, and you can, force it to look like it's ordered and that it's somehow connected, but it's just the way it looks. It's not the way it acts. It's not the way it is. Photons can look like they're waving, but they're not in a wave, and they're not connected to each other, and they're not pulling on each other. They're not doing things like water molecules are doing. It's not the same thing at all.
That travels, that has an electric component and a magnetic component, and it travels, and guess what that is? That's light. So I have lights here.
So he says it is, and I'm saying, well, no, it isn't, and I think I can prove that it isn't. I think a rational analysis of the double slit does explain and make quite clear what really happens. Photons, as Einstein stated, are made out of these energy quanta, and it's just a frequency of these little bits of energy, little bullets at a frequency. So you have to have 3 or 4 of them hit a surface. They have to hit within a polarization at a timed event. It has to be a timed event and an event over a distance on the surface, and those factors will dictate whether the electron is pushed out of an atom and whether an electron is pushed with enough velocity to actually leave the surface of the material altogether. And all of that will be dictated merely by you hitting like a tipping point argument. If you want to tip something over, you've got to hit it while it's still moving in the direction you want it to go. To add energy, the object has to be moving in the direction you wish to add energy in. And if it's going in the other direction, you're not going to add energy to that system. And that's the simple rule. So it's not about having more energy. It's about applying the energy at the right timing. So it's about resonant frequencies and resonant oscillations. And the fact is that photons demand, the requirement is for a photon to be a photon, is that it has to hit in exactly the right time sequence.
They're hitting me, they're bouncing off of me, they're going into the camera. Those are all electric magnetic fields that are oscillating, hitting me, and bouncing off.
So he says so, but he doesn't really have any evidence of so. And again, that can't be unified. That can't be even explained rationally. I mean, as Feynman points out, waves go everywhere. The photons don't do that.
We're going to talk about the wave aspect of light after we talk about electric fields and magnetic fields. Right? And then this is kind of, you could call it physics 4, but I'm going to call it modern physics, which is something you typically see also. Modern physics. And this is actually one of my favorite parts also, because I just find it mind-blowing.
I find it irritating, nauseating, embarrassing, frustrating, creepy. That smart people fall for these preposterous stories. This is Sasquatch science. These features, these functions are so outrageously irrational and disconnected from any kind of real evidence that you're just saying, why would people believe this crap?
The first part of this typically is relativity.
Somehow there isn't real space in space, and somehow nothing can actually be going no speed. Everything somehow has to be going a speed of some kind. No, it doesn't. Speaking of unrelated to reality, the commercials. Jesus Christ. What planet is this? Just amazing.
I'm sure you probably heard about this, and I know that you also probably heard about something called quantum mechanics.
So stuff with singularities, entanglement, many world interpretations, the photon, magically interferes with itself, all kinds of silly, idiotic explanations.
What is all this about? Relativity deals with the fact that's just mind-blowing, but the fact...
He's saying it, right? The fact. No, it's not a fact.
That clocks, things that we think are constant, tick, 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 tick of a clock. Time is not constant.
So, no, time is fine. Clocks aren't constant. Clocks are easy to break. Okay, the measuring device is a mechanical system, and you can move it too fast, you can move it too slow, you can hold upside down, you can put it in the wrong gravity, you can do all kinds of ways to break every clock ever invented. Every clock ever invented has always got a weakness, And they're pretending that atomic clocks don't have any weakness when they have an obvious weaknesses. That you can change the decay rate. You can change what you're measuring, what you're using as a crystal to give you a timed event. You can change it really easily.
For all people when they're moving near the speed of light. So if I have one clock stationary and one clock stationary next to it, and they're ticking in synchrony, right? And then I take one of those other clocks and I zoom them off near the speed of light. When that clock is traveling near the speed of light, time...
So just the very idea that they could ever take a real clock and actually move at the speed of light, that any matter would actually hold up to the process of being moved the speed of light, which means all the force has to be pushing from one side, meaning there's no other movement inside of the atom, essentially, except for the movement in this direction. Then there's nothing to really hold the electrons and protons together. There's nothing, there's very little probability you can hold matter together, matter beyond electrons and protons. Now, an electron and proton will survive going very fast, but an atom's not going to survive it.
Doesn't flow the same for that clock or that person in the spaceship. It flows differently. In other words, the reason it's called relativity...
So again, there's no change in time in the universe. It's the same time everywhere in the universe. And the distance is reliably detected by how long it takes for something to move at the speed of light across the universe. There's really no evidence that anything is in a private frame and that it gets to play by private rules.
It's because things happen differently to different people or different experiments.
So none of that stuff happens. There is no difference in anything that happens except our ability to see something far away. So if it's far enough away, we're not going to see it for quite a while. And so we're not going to see things the way they actually are because of the fact of distance being different. So two simultaneous events can take place in the universe, and if they're at different distances from us, we won't see it correctly. We'll see the one that happened second first, or the one that happened first second. Lots of things can be messed up, and it just has to do with perception. It has nothing to do with anything real.
Depending on how you're moving, how fast you're moving. Now, we don't notice clocks ticking differently because we're not...
We see mirages, we see vapor, do all kinds of things to images. We see lots of distortions in our world. We know distortion happens. Shouldn't surprise us at all. So there's not a subject here. There are no real mirages.
Traveling anywhere near the speed of light. We're traveling at a snail's pace, but that's the way the universe works.
No, it isn't. Says you, blah, blah, blah.
Everything's relative, including the ticking of clocks.
Nonsense. Complete nonsense. Photons only do one thing. They move in a straight line at a constant speed, and they accurately portray distance.
And then we have the idea of quantum mechanics, which we're going to get into a whole lot of detail later, but quantum mechanics is all about the fact that, I told you, electromagnetism was a wave, right? But we also have figured out in the 20th century that it does behave like a wave. Light does behave like a wave, but it also...
So it doesn't explicitly behave like a wave. So that's the big giveaway here, is that it doesn't really, if you analyze it with any kind of rigor, there really is no similarities. I mean, the similarities are so slight and so small, it's nothing like it. So if you look at a platypus and watch its behavior, and you watch a duck for a while, you'll figure out they're not the same animal. And this is the same kind of silly statement, that just because it has webbed feet, it's a duck.
also kind of behaves like a particle, like an object, instead of...
It always behaves like an object in the sense of any behavior we're going to be able to analyze and see. So it's clear it always does.
It has characteristics of wave, but it also has characteristics of being a...
So it doesn't really, it's all explainable as little bits of momentum moving in straight line vectors. You can only bend it by colliding it into electrons and protons and changing its direction. And that's it. There's no other event for a photon or the elements of a photon except collisions with electrons and protons.
Little particle. So is it a particle or is it a wave?
It's definitely a particle. Definitely.
It turns out it's both.
No, it isn't. It can't be both. They're not possible. Silly talk.
We don't have a word for it, but real photons...
I have one. Silly, stupid, crazy, wooey, religion, made up crap. That's the word. Metacrop.
Real electrons, real protons, real tiny particles of anything have wave-like characteristics,
No, they don't. So just stop saying it. It's not true.
and they also have particle-like characteristics.
Yes, that's all they have. Particle-like characteristics.
So it kind of messes with your mind because it doesn't make sense, but it
Well, it doesn't mess with you if you're not messed up. So stop being messed up and then we won't get messy. I mean, it's really, like I said, they're jumping the evidence way, this whole, every time we see an on-off pattern, we know exactly what caused it. Yes, even though it's the simplest pattern in the universe, it could be caused by multiple things, we'll always assume it's interference for no good reason.
it is the way the world works because we have over 100 years.
Says you. So again, more nonsense. You don't have any rational, real experiments. You have contrived and strangled and twisted experiments, barely on the limits of credulity because they rely on you understanding every variable in these convoluted experiments, which you don't, obviously. In my opinion, you don't even understand what a beam splitter is doing, so you can't get the simplest things right.
Years of experiments showing that both of these things, relativity and quantum mechanics, are both, as far as we can tell, absolutely true.
Yeah, bullshit. So that's all I can say is you really haven't analyzed, you really didn't do the experiments, you really haven't done enough experiments, you really haven't tested this thing hard enough. Simple little things you could say. Look, they did the double slit experiment. The idea is this pattern, these fringes should go all the way, the 180 degrees of the spread. They should be creating fringes all across that. So they should have put photographic plates on the two sides and collected some of this fringe pattern that's supposed to be going on these two horizontal planes. It should be hitting those. If I put photographic film here, I should get fringe pattern. Never even tried the experiment. This isn't tested physics. This is just made up religion.
Now what we want to do is jump a little bit more detail. We're going to get in the entire course into so much detail, solving tons of problems, but I want to give you a roadmap to show you a little bit more about these topics, and we're going to get a nice overview of that. So when we talk about...
All right, well, maybe I'll call this part 1, and, yeah, we'll do a part 2. Yeah, might as well finish it out since I started. Might as well finish this video. He does another next one on thermodynamics, and he does another one on the quantum stuff. So, it might be worth doing all of them. And just pointing out how the places where he'll say we've proven or it's a fact and blah, blah, blah. And we have 100 years. It doesn't matter how many hundreds of years you give them. They don't test anything. Again, they still haven't dropped 4 pounds 1 foot and 1 pound 4 feet and seen how big a impact they make. Still haven't done that experiment. So they don't test anything. They just make up crap, build the totem pole, and then they start praying to it. So I think that'll be enough for now. So till the next time, and such and so forth. And I might do a different video in between the parts of this one on see how I feel and such. So till the next time. I think it's really enough. Have to do. Okay. Yeah.